Hey, physics people, let's talk about Einstein writing the graviton. So let's see if I can draw this. Here's our ride, the cylinder, and there's an axis of rotation here. And we have a person sitting right here. Here's our person, legs. And they're like, ah, and they're spinning around. So this thing is rotating with some angular speed, omega. They have a tangential speed v, and the entire ride has a certain radius r, the big cylinder. So let's look at it from the side. And here is the wall, and the thing is rotating out towards us. So here's v, right out of the page towards us, and we're gonna let's make our rider a box because it's a little bit easier to explain what's going on. And here's their center of mass. Let's draw the forces acting on this stationary rider. So this is Einstein, not sliding. Just as a reminder, as the ride is rotating, the net force is actually going to have to be inward or you'd fall down because they drop the floor out in this ride. So if we don't find that the forces are balanced and the person is being held in place against the wall, they're going to fall. So that better be what we discover here. So let's draw the forces acting. So there's mg down, there's a normal force from the wall, oops, and there's friction keeping you from sliding down onto the ground. So you can see that the relationship between force here, let's remind ourselves, friction is mu times normal. And this, by the way, is static. We don't want to slide. So we're making the claim that how hard the wall is pressing in on you and the role of friction is keeping you from sliding. If there's no friction, the wall can be pushing in all you want, but when they drop the floor, you'll be in free fall. You'll just slide and hit the ground. So that would be terrible. Okay, so this is static friction. Let's do the sum of the forces in the y direction first because we want it to be zero. So we're saying friction is up. And oh yeah, let's make some decisions then. Plus y is that way, and we'll call plus x for this particular frame of the video. Plus x is to the right. So that friction F doesn't look great. I'm gonna fix it. So that's friction up and mg down. So friction is actually equal to the weight. But what's the relationship between well, let's keep going. I want to see what other things we can determine. So friction is equal to the weight, but maybe we don't know the other components. Like maybe we don't know what mu is. So let's write down the sum of the forces in the x direction. Well, it's not zero. It's not just ma. It's mv squared over r. And as a reminder, the centripetal acceleration can be v squared over r, or it could be omega squared r. Either one works. So mv squared over r is the sum of the forces. Well, what's causing that? That is the normal force. So what I want to show you is you can actually relate all of these various components together. If we know that friction equals mu times normal, which also equals mg, that means mu times normal, which is mv squared over r, equals mg. So as long as your centripetal acceleration, as long as v squared over r is greater than, well, look, the masses cancel, and we're left with v squared over r equals g divided by mu. But what I'm really saying is if v squared over r is greater than this quantity, all is well. But if g squared over r gets to be less than this quantity, then you've got problems. Your friction will no longer keep you in place. So I'm trying to make sure I'm looking at all the things you might have needed to find. If you knew V and you knew R and you knew G, you could actually find mu this way. So if you were asked to find mu, so mu would be equal to R times G over V squared. That's an important thing to note. And also what we're really saying here is, let's go ahead and make this really clear. V squared over R needs to be greater than or equal to this, or you're going to slide. Okay, so that actually is also helpful for one of the UT homework questions you've been asked this week. And don't forget that omega times R equals V. So that often shows up a lot as well. I think that's probably enough that y'all can now do the Einstein writing the gravitron and the question about weight and spinning around in a circle on the UT homework.